Hi everyone, thank you for coming. We are here today to talk about some work we've done around graphs with Titan and Spark GraphX for analyzing time-varying electrical networks. I'm Guillaume Germain, data scientist at EDF R&D, and this talk is going to be a 2 presentation with Thomas Vial from Octo Technology, a French IT consulting company based in Paris. This talk will be as follows. First, I will start by giving some elements and context about EDF, and I will describe some business cases which have motivated this project. Then I will go over some key concepts and technical aspects of graphs, and I will present Spark GraphX and Titan. Following sections will be presented by Thomas. He will give you some details about algorithms used to process the electrical network. Then he will go over some technical aspects of GraphX and Titan implementations. And finally, as a conclusion, we'll share our recommendations with GraphX and Titan, giving you some guidelines if you want to explore this area. Okay, so let's start with some elements of context about EDF. EDF stands for Électricité de France. It's the historical and main supplier and main utility in France. All aspects of electricity are covered, from generation, transportation, distribution, sales, and trading. EDF is a worldwide company of 160,000 employees for 40 million customers, mainly in Europe and more specifically in France. As a prospective study, all the work presented in this talk took place within EDF Lab, which is the R&D task force of the group, with more than 2,000 people spread out across 10 international centers, mainly based in Europe. Okay, so here you can observe a very simplified view of the electrical network. Basically, the electrical network is divided into two main parts. The first one is a transmission network carrying electricity from power plants to local endpoints called distribution substations. The second one is a distribution network in charge of dispatching electricity toward final clients. For the purpose of this study, we put the focus on the distribution network only. As you can see, the distribution network is itself divided into two subparts, which are medium and low voltage. Combined together, they are composed of 1.3 kilometers of electrical lines with a total of 100 million of technical equipments, and all this network is powered by 2,200 independent distribution substations. There are a lot of different technical elements forming the electrical networks. Main ones are transformers, line breakers, switches, meters, and so on. Okay, so here you can observe a subpart of the distribution network corresponding to a single distribution substation. Electricity flows from the distribution substation through the network until it reaches meters. Typically, this kind of subnetwork contains approximately 50,000 of nodes with a depth of 200, but those figures depend strongly on the area specifics covered by the network. The problem is quite simple as long as we consider only one single distribution substation at a time, because we can modelize it at a simple tree. But it gets more complex when we add another distribution substation with this related network. In such a case, we have to consider the fact that these two networks are physically connected together in case of failure, with one distribution substation helping the other one in providing electricity. But now, you have to imagine that there are not only two distribution substations, but 200 and 2,000 of them, all connected together, forming a global network of approximately 100 million of components. For this study, we wanted to cover a few business cases as a proof of concept. The first one is to provide a way to get a global picture of all powered components at the present time or at any given time in the past. The second one is to be able to track the physical evolution of the network over time. By physical evolution, I mean the addition or suppression of technical equipments from the network. Next, we want to process the electrical energy balance for any subpart of the network and for any given period of time. And finally, in case of an equipment failure, we need to be able to figure out the best way to restore power supply to subsequent components, taking into account the network configuration at this very specific time. So, according to the description of these few business cases, we can realize how important is the modelization of time, of events over time. Okay, so now how do we transpose those business cases towards a more conceptual point of view? First, we have to find a way to define some relationships between technical equipments. And in fact, the main functionality of graphs is precisely to provide a way to easily define some relationships between objects. Then we want to associate some properties to each component of the network, and that's the reason why a property graph is made for. We also want to have a way to explore the network with complex calculations at hand. And here we have a very good candidate with graph processing frameworks. And last but not least, we want to keep track of events across time. We will see that it's not an out-of-the-box process, but it can be modelized through the use of a property graph. So finally, the way to go is quite obvious. Indeed, it's all about graphs. Okay, so now I will go giving you some key concepts and technical insights about graphs. Okay, so a graph is basically composed of vertices and edges. A vertex represents a node, and an edge represents a link between two nodes. So here is a vertex with its associated properties, and here is an edge on which we can possibly add a label to describe the kind of relationships between two vertices. And when we put all these concepts together, we obtain what is called a property graph. In this study, all components of the network are modelized as vertices. For instance, we have distribution substations, line breakers, switches, transformers, loads, and even lines. I insist on the fact that we have also modelized lines as vertices. Indeed, a line is also a technical equipment and not a link between two components. As a consequence, edges represent only symbolic links between components. Moreover, edges are not oriented because of the fact that electricity can flow to one direction and the other way around, depending on the configuration of the network. And finally, it's important to notice that metering data are not attached as properties into the graph, but are managed in separate storage. In this study, we use Hashbase. Okay, time modelization with graphs is not something you get out of the box. In fact, you have to think about a way adapted to your specific problem. For this study, the concept we ended to implement is to grow a maximal graph, applying graph mutations at each new event. We decided to work with time intervals associated to vertices as vertex properties. Each time a new event is raised, a time interval is updated or created. This mechanism is implemented for the three kinds of events we want to track: equipment lifecycle, equipment failures, and reconfigurations of the network through switches change of state. Okay, so here is a more practical example. So to begin, we initialize the graph as a screenshot of the network. For each vertex, we initialize the validity property with a -infinite, +infinite time interval, and a failure property with an empty time interval. Okay, so now let's say that at time t1, a new technical component is added to the network, in this case, a switch. We logically define the validity interval as t1 +infinite, and we can observe two new properties associated exclusively to switches: switch state and default state. We can also do the opposite processes by deleting a component. In fact, we keep the vertex in the graph, but we close the validity interval here with the time t2. Okay, so now let's say we have a failure on a technical component. So in this situation, we define a new time interval associated to the failure property, t3 +infinite. And finally, let's say we want to repair this faulty line. So first, we want to cut the power by opening the switch. So here, a new time interval, t4 +infinite, is set for the switch state property, meaning that the switch has an open state. Thomas will describe in detail how algorithms we developed are handling these time interval properties when exploring the graph. Oh, sorry. Okay. Okay, so now it's time to talk about our two challengers, Spark GraphX and Titan. So let's begin with Spark GraphX. GraphX is based on Spark engine, extending classical RDDs with an edge RDD and a vertex RDD. It's purely a graph processing framework with distributed data and distributed queries ready to process huge amount of data. GraphX offers an API to make some fundamental operations with graph objects and also implements a collection of graph algorithms like page rank, triangle counting, and so on. The core of GraphX is an implementation of Priggle, a very well-known graph processing architecture developed at Google back in 2010. Priggle is based on the bug synchronous parallel mechanism, which is, to simplify, some kind of MPI. Priggle is vertex-centric. Algorithms are developed within vertices, and edges don't carry any computations. Priggle works with a sequence of iterations called supersteps. At each iteration, a vertex can perform some specific operations, like reading messages from previous superstep, executing a user-defined function, or sending messages to the next superstep. Okay, so basically, this is the way Priggle works, schematically. First, each vertex receives some messages processed as the last superstep. Then, a merge function is aggregating all these messages and sends the output to a user-defined function in charge of processing all the logic implemented in the graph. Next, messages are sent to vertex neighbors, and the process can then be repeated for the next superstep. And finally, the vertex can halt itself. It's some kind of term signal triggered when the vertex reaches a specific condition. We'll see that Titan is also using this kind of algorithm when using distributed queries. Okay, so speaking about Titan, here it is. Titan is a well-known graph framework optimized for storing and querying billions of vertices and edges on top of a cluster. It's also made to support thousands of concurrent users and has the ability to process local queries or distributed queries across a cluster. The storage backend of Titan for vertices and edges can be indifferently Cassandra, Hashbase, or BerkeleyDB. Titan is tightly integrated with Gremlin, which is an agnostic graph traversal scripting language. When used with Titan, Gremlin queries offer the possibility to be processed indifferently, locally, or across a cluster. In the case of a distributed query, Gremlin leaves the choice of the engine backend, which can be Giraffe, Hadoop, or Spark. Okay, so now let's talk a bit about Gremlin. Gremlin is a graph traversal scripting language, and is part of Tinkerpop. Tinkerpop is an open source project composed of several components, all related to graph management. It's a widely supported library, pluggable with graph databases like Neo4j, R&DB, Spark-C, and so on. Tinkerpop connects to graph databases through the blueprint component, which is like a JDBC driver for graphs. So when we consider all the processing chain, we have Hashbase as a storage backend for vertices and edges. We have Titan as a graph database, and then Blueprint as a driver for connecting Titan and Gremlin together. And finally, Gremlin for processing queries over Titan. And on top of that, we have to keep in mind that Gremlin can perform some local graph traversal with non-distributed queries, or large graph analysis with queries distributed across a cluster. Okay, so now I will pass the floor to Thomas, who is going to explain in details how we implemented algorithm with GraphX and Titan.
Thank you. So starting from here, Guillaume has shown you what various frameworks we are using in the project. I'm going to focus more on the algorithm side in the first time to show you how we can use those frameworks in a situation where the graph is varying over the time, which yields another level of complexity. So for this purpose, we we scratched our head and thought how to model the time. That's what Guillaume presented with the property graph, and how to use this graph data model in an algorithm, a traversal algorithm. In our case, our use cases have specific properties which are interesting for us, algorithmically speaking. Sorry. The use cases we want to implement have as input a period of observation, which is a time interval, T1, T2, and a particular vertex as a starting point, typically a distribution substation for which we want to compute some statistics, for example. And we know for each vertex in the graph, its validity and failure intervals, and so on, representing its state at any given time. And for a purpose, we want to traverse the graph, that is, explore the graph from the input vertex until we reach all the subgraph that is lying under the vertex. And for this, we devised what we call the trickling algorithm. I'll explain in a minute why the name. And the advantage of the algorithm is that it can be implemented quite easily with either Gremlin or Pregel-like paradigm, GraphX. So the trickling algorithm. In the more general form, we have a graph or a subgraph linked to a single source and a period of observation, T1, T2. And we want to explore all the path going from source S to below the source. For this, we consider the vertex activity, failures, and so on intervals, which we merge into one single validity interval per vertex, here represented as gray and green shades. Green meaning the vertex is active, and that it means that the power can flow through the vertex. We first take the period of the observation, we inject it into the source, starting point of the exploration, and we perform some arithmetic interval on it. That is, we perform the intersection between the period of observation and the activity intervals. That gives a resulting set of intervals, which is the actual flow going through the vertex, the source. And we put this resulting interval, we push it down the graph through the edges, and we apply the same mechanism with the validity intervals of the next vertex, and so on. At each step, we perform the intersection, and we compute the actual flow that each node has, the flow that reaches each node of the graph. And in the end, we have all those sets of intervals which represent the times when the node was powered. So it has a direct representation with the case we want to see. So this is the general form, and now we'll see how it transposes to the use cases we want to implement specifically. For the first case, which is get a picture of all powered components at any given time, we just take as the input period, we take a very small interval, typically time t and time t plus epsilon, where epsilon is, say, 1 second or 1 minute, whatever. We perform the trickling algorithm, that is, we compute the actual flow, and we get, as a result, the same input interval whenever the node is powered. When we have an empty set, that is, for example, here at the bottom, it means that the equipment at time t was not powered because the power did not reach it. So we can acknowledge the state of the vertex, and that means getting a picture of the network, the subnetwork reachable from source S at time t. So we get the immediate results we wanted to achieve. The second use case is not that much complex, actually. This time we have a period of time, a complete period of time, and we want to track how long the equipments were powered. We compute our actual flows, which yields, as usual, lists of intervals, and we simply sum up the length or the width of the intervals together. And we can, if we compute a ratio against, for example, the period of observation, we can yield a percentage given the proportion of time when the node was powered. We can, for example, relate this to some SLA against the powering. And we have the immediate metric. So you see, the first use case was getting a snapshot of the network at a time. This use case is different in that we perform some aggregation, some business intelligence over the graph, taking into account the time, the fact that the graph evolves in time. The next use case, if we want to manage the energy balance, it's a bit different. Again, we perform our calculations. We're only interested in the meters here, which are the leaves of the subtree. And we combine this information with the load curves that we get from the curve store mentioned earlier. That is, the load curve, if you're not familiar with it, it represents the consumption, the power consumption of the end consumer at the end of the network. So given those curves that are expressed in kilowatts, if we compute the area under the curve for the intervals that when the equipment was powered, we get the energy that the equipment consumed during this period of time. And when we sum up all those equipments reachable from the source S, we get the total power that the source S had to supply during the interval T1, T2. And so we can track how much the source S was stressed, for example, if the network was imbalanced. We can see this through this kind of metrics. So far, 3 queries, 3 direct applications of the trickling algorithm. So we're happy. The next, before we see the next use case, the last one, we'll show you how it looks like in code very quickly. We're not going through it very deeply, but just to give you an idea. If we want to do this with Gremlin, we only have to write 30 lines of groovy code. This is the core trickling algorithm expressed in the Gremlin language. So you see it. We can compare it to some SQL for graphs, just to give an idea. It's very simple. It's very legible too. It's basically a loop, and you say, okay, loop over the network until you reach the leaves and perform some calculations at each step, and that's it. Actually, indeed, the calculation is propagating the validity intervals and doing the intersections at each step. If you want to look at a particular application, here it's the energy balance, the aggregated load. We simply call the function that which is the core of the trickling algorithm, and we apply it with a particular computation, which is comparing them with the load curves. So again, 20 lines of groovy code. So for a total of 50 lines of groovy code, we have our use case, which is not so bad. Okay, if we want to look at the same code for GraphX, so this time it's different, it's in Scala. You see that Pregel gives us all the framework and all the heavy lifting of passing messages, which are in this case intervals. And in on the same amount of code, we have our use case again. So we're happy. Scala is more complex than Groovy. It's less agile. We have to compile the program and so on. I personally prefer Groovy, but that's it. It's not a big deal. Okay, it's time to see the last use case. I put it aside because it's a different implementation. Here, we want to restore power supply after a failure, which means the first thing we need to know to do this is what is the backup substation for any given source. So in this case, I want to know if this source and the equipment below this source fail, how to restore power to those consumers here, which are below S. The thing is, there is a link between the switches here, which means that the backup substation is S prime, and my query wants to find S prime given S and the network. So here we're not interested in time intervals. We're doing some static analysis on the graph because it's how the infrastructure is designed. And it's a kind of pattern matching, very easy actually. You start from the substation S, the source, You're okay. Let's go through the edge. We found a line. Let's go a little bit more. I found a switch. Okay, let's take the path backwards. I found another switch. I can find many other things in between. And if I go up again, I eventually reach a substation. So the pattern here is substations, substation, lots of things, switch, switch, lots of things, and substation, taking into account the direction of the edges here, because it's designed this way. It's simpler this way. And let's have a look at it. In Gremlin, it's very short again, but it's more complex. The thing is, you have to remember quite precisely what you wanted to do, because it's not very legible after a while, unfortunately. So I put a lot of comments in there to try to explain what each step does. But that's it. With this, it's pattern matching against the graph, and it's quite interesting as well. A bit more tricky to implement, but that's it. We did not write this use case with GraphX, so I have no code to show you. My guess it would be a lot trickier because we're using a subset of Gremlin that is specifically designed for pattern matching, and it gives a great amount of ease for this. Okay, let's see how it gets when we scale. Here, in the case, we have a model of the actual graph, which is 100 million vertices and almost the same amount of edges, which it's a very good representation of the actual network. And we loaded this on a 10-node edge-based cluster for the. It's just for the anecdote. We have roughly 50,000. Equipment under each source, as Guillaume explained before. And for information, the Titan table, the resulting Titan table, is made of only 3 regions, and the queries there are equally distributed, which means Titan's data model is quite efficient regarding edge-based storage. And we measured the unit execution times. It's a kind of a very cheap benchmark. The approximate time for the first use case, get the powered component, is 1 minute. Good. For interactive querying, that's not so bad. The aggregated load for the energy balance, 2 minutes. That's not so bad. Finding the backup substations, that is the pattern matching, 1 minute. Yeah, that's good as well. Very good. Still, when we do this, we're only looking at one substation, one source, and performing the query, executing the query for one source. An operator dealing with the whole network, we would like to have the global situation of the network, so we see how it scales when we run more queries over more sources. Okay, so for this we took the lazy path. We simply run queries in parallel, each query relating to one source. This is one line of groovy with gparse. It's very easy. The architecture, just to be clear, is the following. We have our queries, which are each one is a thread. We have our Titan and Gremlin framework API in the client node, so everything is executing in memory here, and the edge-based cluster holding the Titan data. Very simple. And if we plot the execution times against the number of sources, that is the number of threads, we get this. So the scale is almost linear. The hills here, or the steps here, are just the fact that it's a 24-core machine and that threads are executed in waves. The parallelization framework simply enqueues the threads and runs it whenever possible. Actually, it's a very predictable time. If we model this through waves of 24 threads, including hyperthreading, we would get exactly the same curve. So the information here is that the execution time is predictable. Still, we have a problem because at 80 stations, substations, sorry, we get an execution times of 400 seconds, which is way too long if we want to get in an interactive view of the whole network. We cannot afford to run the same query 2,200 times and wait for the result. So here the Titan's OLTP interface has a limit, obviously. That was expected, by the way. That's why we wanted to try a Titan OLAP and see if we can, for example, pre-compute the situations of the whole network in advance and storing the KPIs somewhere on the database pre-computed and just have to query them. So that's good. Thing is, it's not that simple. We were very eager to do this, but we had some trouble in that Titan and Tinkerpop, as Guillaume said, are very tightly integrated, and things are moving around between the two. We have some portions of code that are going from one framework to the other, or the other way around. We can download Titan and run Titan. We just have to update the HBase connector, but that's nothing. Or we can download Tinkerpop and put the Titan jars in there. Anyway, we get you quickly fall into the ClassPass hell problem. And even if we could make this work, we had another choice to make, which is, are we using Giraffe or Spark backend for Titan OLAP? I hope it's still understandable because it's very complicated actually. And basically we couldn't make it work. That's it. Our understanding is be patient. Titan is improving the Hadoop 2 support, which is not there yet. We understand it's the main reason why we couldn't make it work, because you have some jars that's ongoing. You have to tweak the jars, and it's a mess. Hopefully, in a few weeks or months, things will get more stable, and Tinkerpop and Titan will be more cleanly separated. I don't know. At least I hope. So yeah. GraphX, which was the other candidate, if you remember. GraphX, we didn't have the time to benchmark it yet. So if you remember, we only tested the algorithm. We implemented the algorithm and did a proof of concept with it, but we could not, at the time, run a benchmark. Just didn't have the time yet. Thing is, Databricks has announced the release of GraphFrames, which is clearly a competitor to GraphX, or maybe some layer running on top of it. It's not clear. So we don't really know what the situation is at the time. Maybe we have to change our minds. Another layer of complexity. As a conclusion, okay, that was a lot of information. It was a bit dense. We understand this. The conclusion is we're at a turning point for graph analytics. Think Aurelius, which is behind Titan, has been acquired by DataStax. So the question is, will DataStax continue to support HBase? At what pace? We don't know. Hopefully, yes. Titan and Tinkerpop are undergoing some refactorings, which are hindering us. There is improvement in the computation backends, more support for Giraffe, etc., and for Yarn, but it introduces another layer of instability, unfortunately. And GraphFrames, which is the new challenger here in the picture, and we don't know yet if GraphX is doomed or if it will continue to improve. We don't know. But the bottom line is that graph analytics are becoming commodity. As you can see, if you know Groovy and you learn it very quickly, you can start projects very quickly, and this is a good thing. Another thing, to be on a lighter note, some recommendations. After this study, we have a clearer understanding of the situation. A Titan OLTP interface is good for interactive querying, but for a relatively small number of vertices. 50,000 is good. Beyond, it gets the times are becoming prohibitive for an end user. Titan OLAP, it's obviously a very good candidate to perform the computations in advance, perform KPI computations. But wait for Hadoop 2 support. It's not there yet. Hadoop 1 is not supported anymore, so it's no point in running it. GraphX for the same usage, of course. GraphFrames, we don't know, it's too early yet to have a clear vision on it. Anyways, if you are making a choice, be sure to test everything thoroughly in your environment. It's very important because it's very complicated. You have all those frameworks going together. You have Hadoop in the middle. If you're using Spark, you have Scala, which has its own level of complexity. You go deep, deep, deep into JVM, class path issues and debugging. It can be very time-consuming. Or maybe wait a little bit until it gets clearer, hopefully. That's it. Thank you. Question time. Yeah, over there.
You spoke a lot about graphs, but you never showed us any. Can you show us some examples?
We have a graph. That's unfair.
These are the outputs from your analysis. I thought this was a...
No. Oh, sorry. My bad.
C'est en mode.
Ouais.
J'en ai un.
Spinning wheel.
Il y a un vieux message là-dedans en fait.
Ah. Okay, sorry. Okay, there was a graph actually. I perfectly remember it.
I can get it here if you want.
No, it's okay. I think it's back.
Ah,
Thank you.
ok, thank you.
No,
Okay.
Well, that one. Does it qualify as a graph for you?
Yeah, fair enough. I just meant it's just the outputs from the algorithms it shows.
No.
So it's all about graphs, so can you show us the outputs from those? How?
Oh, no, the output is just it's still POC. We have no UI. The output is simply a list of vertices or a number of vertices showing that we traversed the graph, or a figure if you compute to KPI. That's it. Okay. Yep.
Well, in your use case, it's more graph traversal. You have to explain. But GraphX is more for graph processing, so that's really for traversing the graph. So you need to explicitly define the starting point and defining a stop policy, defining when you have to deactivate nodes. So do you think that GraphX is a good fit for that?
Yeah, because the starting point, actually, you initiate the algorithm by sending a seed message to all vertices. So, for example, each vertex has an ID. And if you say my starting point is ID 1, 2, 3, vertex 1, 2, 3 will consume the message, the other ones will ignore them, and we process. Here, in this case, we're very lucky because it's almost trees everywhere, except for the crosslinks. So the stop condition is obvious, is when I have no outbound neighbors, I stop. I vote to halt, and when everyone voted to halt, the super steps end. Does that answer your question?
Yeah.
Okay. There was a question there.
I was curious about, it sounded like you couldn't scale up or make your algorithm run fast enough to get to your 2200 nodes, but did you stop to think how much hardware would I need to buy to just scale the hardware up?
No, we did absolutely no tuning. It's a very early POC. I was rather surprised in a good sense when I saw that in 30 seconds, 1 minute, I could get a result, considering the size of the graph. But obviously, there's lots of room for tuning in edge-based memory, in pre-region splitting, for example, to have more regions more spread across the cluster. Lots of room for improvement. Still, the OLTP doesn't scale, that's for sure.
How
That's
big
for
was
sure.
the cluster that you were running this on?
The hardware spec?
What was the cluster that you measured?
Oh, it's a 10-node cluster. But actually, the three regions were in on one single node. That was for the record, actually. No, it's a graph itself is very compact.
Yeah.
All the big stuff is the load curve. They are stored separately, so we don't consider them here. So, right? Yeah.
If you had scaling issues and you obviously kind of put a graph into essentially a non-graph, why a non-graph DB? Was there any reasons why you didn't look at things like Neo4j for that?
I'm sorry, I didn't get the name of the product.
Is there a reason why you didn't look at dedicated graph databases
like, for J and stuff, which can cluster as well. Was it a scale issue? Was it you just didn't know?
Okay, the question is about using graph databases that scale. Well, Titan is supposed to scale, so that was the whole point is in using it. The performance is very tightly linked to the whole architecture. Here we have one single client node running Titan and doing some queries against the edge-based cluster. So each traversal basically is an edge-based query. In theory, we could have lots of Titan processors in parallel and some, I would say, scheduling code that would call all those Titan processors independently and merge the results. We have lots of creativity here. We just simply didn't test it this way, but again, it's another level of tuning. Yeah.
But you didn't have a look at something like Neo4j?
No. Yeah.
For the Titan collab, no possibility of using Phoenix on edge-based?
Okay, the question is about using Phoenix on the Titan OLAP use case. A Titan brings its own data model. So the edge-based rows have a model which is quite opaque. We cannot use it for or custom analytics, for example, because it's not immediately legible. It's like a serialization format. Yeah, if you have time, yeah. Oh, yeah. 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 Okay. The question is, the trickling algorithm assumes and benefits from the fact that below a source there's a tree, basically a tree, and that there's a single path to every node. And is it specific to the electrical network? Well, I don't know if it's specific to electrical networks, but that for sure is something that is very useful in our case. It's a major assumption. It's not strictly a collection of trees, but at any one time, an equipment is powered by one and only one source. So if you take a snapshot at any given time, yes, you have a collection of trees. Even if the crosslinks make the things a little blurry, but it's very useful for us because we can traverse the graph. The length is bound by the diameter of the graph, which is not that big. So it's very useful, and with a different kind of graph, a more connected graph, the algorithm would certainly don't fit. Yeah. Okay. The question is about comparing Titan with other products. I can say we did some comparison with NetworkX, which is very different because it runs in memory. Yeah. No.
We have a study in another department in EDF with Neo4j, but Neo4j is a graph database, so queries are not distributed. Only data is distributed across some. Sorry, my mic is not okay. It's working. Only the queries are distributed across some nodes. Data is distributed across nodes, but queries by themselves are not distributed across machines. So, in case of big graph computation, it appears that Neo4j can't handle large graph processing on a big graph. It's a good solution for medium-sized graphs, but if you go with a big graph, maybe we'll have trouble with complex computation.
Well, it would be interesting to try anyway, but
the
thing is we're missing time.
You mentioned that for modeling the time variation, you basically put in every component in the lifetime, the validates in the graph. So that means basically over time, the graph will become bigger and bigger and bigger. Do you expect any scalability issues there? Or is it just by scaling out then the storage, the H-base in the back end? Or is the, I don't know, that specific problem maybe doesn't grow that fast, but there are also applications where such modeling of time variations actually becomes a problem.
Okay. Yeah. The question is about the graph getting bigger and bigger as we enrich the maximal graph, which by definition only grows. The number of vertices itself doesn't grow very quickly because it's you have a new vertex, for example, when you connect to new equipment. That is when EDF brings in a new customer. So it happens. It happens, of course, but it's not that often. The volume comes more from
Events.
from the events because the intervals grow. We store the list of intervals in the properties of the graph. That is, they are not stored separately as it's the case with the load curves. So yeah, maybe at some point we will hit a scalability issue. So far, not. But,
And just for events, we have approximately 600,000 events per year. So it will grow, but with events. So not with vertices or edges, but like Thomas said, but more with events.
And we're still bound by the diameter of the graph, which is a physical limit on the number of steps we have to traverse. Yeah.
The question is, what is basically the limiting factor for scaling out the graph size? H-base then for you, or?
I would say H-base, yeah. That's a rough guess, obviously, because Titan can be distributed with a bit of architecturing work, of course. But I would guess, yeah, H-base, but with a proper tuning, which is complicated. But with proper tuning, we can probably handle it anyway. Yeah, welcome. What?
How big is a vertex
How big is a vertex in terms of
in terms of
bytes?
megabytes?
It's basically an ID, a name, and 3 properties, plus the intervals. So I would say, yeah, around a kilobyte. Yeah. Yeah, I would say a kilobyte with all the properties. Again, that's a rough guess. Yeah. Thank you.
Thank you.